Hello, welcome to another lecture in the course on 3G 4G wireless communication systems. In the last lecture, we completed our discussion on the log normal shadowing, and we said given a median path loss PL50, that is the 50th percentile path loss, the probability that the path loss is greater than the threshold gamma is given as Q gamma minus the 50th percentile path loss divided by sigma, where sigma is the deviation of the log normal shadowing. And we had also seen an example in which the median path loss is 167 dB with a variance of 6 dB, and we wanted to compute the threshold gamma such that it exceeds the threshold only 5% of the time, which means a reliability of 95%. And we said the margin required for that, the margin that has to be accounted for this reliability factor at the transmitter is 10 dB. Next, we moved on to the computing the noise power, receiver noise power, which is essentially given by the product of the noise power spectral density eta naught times the bandwidth B, and we said the noise power spectral density eta naught can be computed as K times T times B, where K is the Boltzmann constant, T is the temperature, and F is the noise figure. All right. So, we said eta naught can be computed as K T F. All right. And then we moved on to a link budget analysis, which is essentially putting all these factors together. A link budget is nothing but a systematic listing of the losses and gains in this wireless communication system, which can be listed as follows. That is the transmit power PT plus transmit gain GT minus the path loss L50 minus the margin MdB plus mobile receive antenna gain GR minus cabling losses LRC minus receiver plus noise interference N plus I, which is equal to the required SNR. So, what it says is transmitted power plus all the gains minus all the losses is equal to the received power or the received SNR, right. So, it is a very intuitive and simple formulation of the link budget analysis, and then we have looked at an elaborate example of the link budget analysis comprising of several components, that is the path loss, the margin, and so on and so forth. And finally, we had listed these different components in the link budget, which is we have to compute the transmit power. Given the transmit antenna gain is 12 dB, the median propagation loss is 167 dB, margin is 10 dB, and receive antenna gain is 5 dB, cabling loss is 3 dB, receiver noise plus interference is minus 151 dB, and the required SNR is 37 dB, which is essentially the SNR that is required for BPSK decoding with probability 10 power minus 4 in this wireless communication system. Hence, with this understanding, let us now complete this example, which is essentially as follows. Hence, I can write from the link budget analysis, we have from the link budget analysis, we have PT plus 12 minus 161 minus 10 plus 5 minus 3 minus 151 equals 37 dB, which is the required SNR. Remember, 12 is the transmit antenna gain, 167 is the median path loss, 10 is the margin, 5 is the receive antenna gain, minus cabling losses, which are 3 dB, minus receiver plus noise interference, which is minus 151, equals 37, which is the required SNR. And now the received required transmit antenna power can be computed as 37 minus 12 plus 161 plus 10 minus 5 plus 3 minus 151, which is equal to 49 dB watts. Hence, this is essentially the computation of the required transmit power at the base station from the link budget analysis. So, this is the required transmit power. This is the required transmit power at the base station. This is computed from the link budget analysis. Hence, the link budget analysis and different aspects of propagation modeling, the log normal shadowing and everything can all be put together to essentially come up with a comprehensive design of a wireless communication system. That is, what is the transmit power required, so on and so forth, to account for these different factors. Essentially, how do you plan a cellular system, what is your power requirement, and so on and so forth, essentially, right. So, this completes one aspect of modeling of the cellular system. The other aspect that we have to talk about in this course in modeling any cellular system is actually the frequency planning, which essentially talks about how many channels are available in a different given cellular system, and how do you plan these channels such that the users are the user demand for calls, or the user demand for placing calls in this system, or the user demand to be connected is satisfied, which is essentially you meet the demand for the traffic from the user's perspective. That is, if you consider these calls or this information, this data that is being generated as traffic in your network, how do you model this traffic, and how do you essentially satisfy the demand for this traffic? That is essentially what we are going to consider in the next part, which is essentially very critical in the design of any wireless communication system, for any cellular wireless communication system, which is essentially the topic that is known as teletraffic theory. So, the next topic that we want to talk about is teletraffic theory, where essentially we say that cellular systems, how do cellular systems meet the demand for traffic that exists in a wireless cellular system? They employ the principle of trunking. So, in teletraffic theory, what we are going to talk about is the principle of trunking, and cellular systems employ the principle of trunking to provide services to a large number of users. Or meet the demands, essentially meet the communication demands of a large number of users. Alright, so cellular systems employ trunking essentially to meet the demands of a large number of users. In fact, this principle of trunking is not unique to cellular communication systems. In fact, this is borrowed from the landline telephone systems, or what is termed technically as PSTN, that is a public switch telephone network. So, they employ the principle of trunking to meet the demands of a large number of users, but with a very few channels, with a number of channels significantly lower than the number of users, with a limited number of channels. So, trunking is nothing but the principle where the demand for traffic, where the traffic or the demands of the users or a large number of users is met with a very few or a very limited number of channels in the communication system. Namely, it can be used in PSTN, or it can also be used in a wireless cellular system. Remember, in wireless cellular system, the available frequency bands or the available channels for communication are severely limited. Hence, whatever few channels are there or are available have to be used by a large number of users essentially. All right. For instance, to illustrate this principle, let us consider that there are 100 users. So, consider there are 100 users in the system. Consider 100 users in the wireless communication system, then let us say these are the 100 users which we are denoting by these points. And now let us say there are 100 channels available for these 100 users, that is there is one channel available for each user. These are 100 channels which are essentially frequency bands or time slots so on available for 100 users. Hence, what we are saying is there are 100 channels that are available for these 100 users. However, remember, now if I have 100 channels for 100 users, that is each user has his own channel. However, this is a tremendous wastage of resources, because at any given point of time only a very few number of users are actually connected to the system, or at any given instant of time there is not all the users wish to be connected, or there is no traffic demand from all the users. There are many users, only a fraction of all the users or all the people who are subscribed to this system are actually connected, which essentially means in a cellular system, out of the large number of subscribers in the system, only a very few users are actually on a call talking to someone or on a data call and so on and so forth. Hence, what this implies is this results in a tremendous wastage of resources. Hence, such a fixed allocation or such a dedicated or such a one-to-one allocation of channels, or such a one-to-one or dedicated channel allocation results in wastage of resources. It results in wastage of resources, as the probability of all users being active, as the probability that there is traffic from all users at any given instant of time is very low, as the probability that all users are active at a given instant of time is very low. Hence, if we have this one-to-one allocation, what we have is we have one channel for each user, that is any user who wants to place a call can place it immediately. However, this results in a tremendous wastage of resources, because you have one channel on hold for every user, and at any given point of time very few users actually would like to place a call, which means all the rest of the channels are lying vacant or empty. Hence, this is not an efficient model for resource allocation or resource provisioning in this cellular communication system, because the probability, if you look at it statistically, the probability that all the users would like to use the channels, in which case this would be useful, is very low. All right. Hence, what we are saying here is only a very small fraction of users in the given system are likely to be active at any given point of time, which means only a very small fraction, only a very small fraction of subscribers are likely to be active at a given point of time. Alright, so only a very small fraction of these users are likely to be active at any given point of time. Hence, what that means is practically very few channels are necessary. If there are n users, you don't need n channels to cater to the demands of these n users. You need only a very few channels to actually meet the demand, because only a fraction of these n users are active at any given point of time. Hence, speaking practically, only a few channels are necessary to meet the demands of users as they are random in nature. What we are saying is the desire to place a call, or the desire, or the event that this traffic arises from particular user is a random event. Alright. So, because this is random, we can now talk about the probabilities, and the probability that all users have to place a call at the same instant of time is very low. Alright. At any given point of time, these are random instances. Hence, these happen randomly. Hence, randomly a different set of users would like to place a call. Hence, the probability that all users would like to place a call is very low, and these events that the users would like to be connected to the network would like to be connected to the base station to place a call is random in nature, and the probability that all the users would like to do that is very low. And this random nature of placement of calls can be essentially used to efficiently allocate resources through a principle which is known as statistical multiplexing. Hence, you are multiplexing these different users, that is, you are using the same references, same resource or frequency bands to multiplex all these users, that is, transmit all their information or place all their calls. However, you are multiplexing them statistically. Hence, this random nature for the demand for communication or basically the demand to place a call is exploited by statistical multiplexing. This is exploited by this technique termed statistical multiplexing, which essentially says that you can statistically multiplex all these users because the placement of calls is a random event, and this statistical multiplexing can be used to support a much larger number of users with actually a very few channels, and in fact that is what we are going to see. How that is possible is what we are going to see in the rest of this topic. So what is statistical multiplexing? So if you were to ask the question, what is statistical multiplexing, let us start defining statistical multiplexing, which is essentially, let us say I have the same 100 users now in my system. I have the same 100 users. I would like to have only a few channels now to multiplex all these users. Now I no longer have a large number of channels, but only a few channels I have only a few channels to multiplex these 100 users. Let us say I have about 10 to 15 channels, alright. I have 100 users, but I only have about 10 to 15 channels to multiplex all users. This is termed as statistical multiplexing, where you are essentially using the statistical properties of the traffic to multiplex a large number of users. This is termed as statistical multiplexing. This is termed as statistical multiplexing. As a large number of users share very few channels. This is termed as statistical multiplexing, as a large number of users share a very few channels, and in the context of cellular systems, this is essentially termed as trunking, where the multiple users in the context of cellular and communication systems, this is termed as trunking, where a large number of users share of the very few channels, that is frequency bands or the number of lines that are available in the cell or at the exchange. So in the context of communication systems, this is termed as trunking. And how does trunking work in a cellular system, which is our concern? In a cellular, if you use trunking, essentially large number of users, very few frequency bands or very few channels. Large number of users can use a very few channels. In the context of a traditional telephone exchange or a PSTN network, landline or a PSTN network, which essentially stands for public switch telephone network, I employ trunking, and this is how trunking originally began. I have a large number of users who use a very few lines available in the exchange. And that is what gives rise to the nomenclature that was used in the old days, which refers to it as a trunk call. A trunk call refers to nothing but there is a trunk of lines which contains very few lines compared to the number of users. Hence, you have to wait for your turn on that trunk, because you are allocated line sequentially on that trunk. Trunking is nothing but they are saying that there are a small number of lines and a very large number of essentially users that you are essentially supporting using this trunk. In the context of cellular system, it becomes all the more important because over the air frequency resources in 3G, 4G systems, 2G systems, all systems are limited, that is these frequency bands and so on and so forth are limited. Hence, it is not possible to have an unlimited number of channels or the number of channels that grows proportionally to the number of subscribers, because the number of subscribers is literally of the orders of hundreds or thousands. Alright. So, how to deal with that in every cell is that if you have a large number of subscribers, you have only a very few channels, and then you statistically multiplex these users as per the demand for traffic, and this is essentially termed as trunking, which is essentially very important in a cellular system to allocate channels to the users. Okay. Hence, however, notice that since the number of channels is much smaller than the number of users, there is always, the probability is small, but there is always a finite probability with which a user can be blocked, because let us say there are 100 users and let us say there are 10 channels, there is some probability with which 10 users are active, and now if the 11th user tries to place a call, he is going to be blocked. Hence, no matter, but the probability of course will be small, but what is said is that there is always a finite probability with which this 11th user is blocked. So, however, since the number of users, let me write this down, however, since the number of users is much greater than the number of channels, since the number of users is much greater than the number of channels available in the cell, there is always a finite probability the finite probability is the key here. There is always a finite probability, there is always a finite probability that all lines are occupied. Hence, what it means is, since the number of users is much greater than the number of channels, there is always a finite probability that all the lines in this cell or all the lines in this cellular system are occupied, which essentially means that hence a new user request, if now a new user places a request for a channel in this state or in this situation, his call is blocked. Hence, when a new user requests a channel for communication, hence when a new user requests a channel for communication, his call is blocked, that is there are no channels available to place his call, hence this call is termed as blocked or his access is denied. Hence, for communication his call is blocked as there are no channels available for communication. Alright, so his call is blocked in the event that all the available channels are occupied, and this is termed as blocking probability, which is the characteristic feature of any trunking system. This probability this probability with which calls are blocked is termed as blocking probability, and this is a very important parameter which we would like to compute. This is nothing but the blocking probability, that is the probability that if a new user, if a user I place a call, what is the probability that all the channels are occupied and that my call is denied. This is termed as blocking probability, or in cellular systems also termed as grade of service, and this is a key parameter, blocking probability or grade of service, which essentially says that users are blocked when all channels are occupied. Users are blocked when all For instance, let us consider a trivial example. Let us say there are 100 users, but let us say there are 1000 channels. Hence, the number of channels is more than the number of users. Hence, the demand of any user for a call will always be met. Alright. So, in that case, blocking probability is 0. But consider a situation in which there are 100 users, but there are only 10 channels available. Alright, which means that if all the user, or which means if greater than 10 users decide to place a call, which happens with some probability, then the 11th user who wishes to place a call will be blocked. And as you can see, as the number of channels increases in this system, the blocking probability progressively decreases. For instance, if you have 50 channels, then the blocking probability is much lower, and when it increases to 100 channels in this system, since there are 100 users, the blocking probability is 0. So, as the number of channels that are there in this system, provision for this system increases, the blocking probability decreases. So, the performance is essentially, it is a trade off. If you want to have a low blocking probability, you need more channels, but more channels are expensive and resources are not available. So, it is a performance versus price trade off. You would want to get the optimum performance at the optimum price that you pay for acquiring these channels or these communication channels, which are essentially the frequency bands in a cellular communication system. Alright, so it is a very important. So, frequency planning and management is actually a very important part of any cellular setup, cellular communication system setup process. Alright, and this blocking probability, which is the key parameter of this cellular system, is what we want to derive using the teletraffic theory. So, blocking probability is a key parameter of a cellular communication. Blocking probability is a key parameter of a cellular communication system, and this is what we have to derive, and this can be essentially derived using teletraffic theory, and we would like to do this. And blocking probability can be derived, that is, we would like to characterize this blocking probability, which can be derived using this blocking probability can be derived using teletraffic theory. And this teletraffic theory, it was first proposed by the Danish engineer Erlang in 1917. Alright, so this was, it was first proposed, this teletraffic theory was first proposed by the Danish engineer Erlang in 1917. All right. So, this blocking probability is what we would like to derive, which is otherwise the grade of service in this wireless communication system or the wireless cellular system. It was actually first derived by Erlang in 1917 in the context of trunking for landline telephone systems, that is PSTN, which is the same theory that we can use in modern wireless communication systems. Now, which essentially means we have to start by characterizing traffic, that is how do we characterize the demand for to place a call by these different users. So, hence first we have to start by characterizing traffic, which is traffic which essentially characterizes the traffic in a wireless system, characterizes the demand to place a call by these different users. So, how do we measure? Our aim is as follows. Our aim is to measure or characterize the traffic in the cellular system. Our aim is to measure or characterize this traffic in this cellular system. The per user traffic is measured as follows. The traffic per user is defined as follows. Which is essentially defined as A naught equals user call rate into average call duration. So, the traffic per user, which is A naught, is measured as A naught equals, which is the user call rate into the average call duration, and this is nothing but the traffic per single user. So, as you can see, this traffic increases if either the user call rate increases, that is the users are placing more calls, that is users are frequently placing calls, or the average call duration, that is they are not placing they are placing fewer calls, but the duration of each call is longer, and naturally it is proportional to a product of these two things, which is essentially the traffic per single user. And now, for instance, consider the following example. Consider a call rate, consider a per user call rate. For instance, consider a per user call rate of 2 calls per hour, all right, of average duration 2 hour, of average duration 2 minutes each, okay. The traffic per user A naught is now nothing but the call rate, which is 2 calls per hour into the average duration, which is essentially a minutes I have to convert into hours, which is 2 by 60 hours, which essentially is nothing but this is 1 over 15. If you compute this, this is 1 over 15. Now, if you look at this, and this is average duration, hence this is hour per call. Hence, if you look at this, these units they cancel out and the traffic is actually a dimensionless quantity. If you look at this, this is actually a dimensionless quantity. However, this traffic, similar to a dB like quantity, this traffic is measured in units of Erlangs. We said 1 call per hour into 1 hour per 1 call per hour into 1 hour per call. We say it is measured, this dimensionless quantity is measured in units of Erlang. Hence, we write this thing here. Hence, we say this traffic. Hence, although strictly speaking A naught, that the traffic is dimensionless, it is assigned the unit of Erlang. Hence, traffic is measured in units of Erlangs, which is denoted by the capital E. All right. For instance, in the above example, the traffic is 1 by 15th Erlang. All right. So, in the above example, the traffic is 1 by 15th of an Erlang. Now, we can compute the aggregate traffic, which is the traffic given large number of users. Let us consider n users in the system. Let us consider the aggregate traffic. Consider n users in the system. Consider then users in the system, then the total traffic now is given as is nothing but number of users into traffic per user. That means we are saying the traffic per user is A naught. If the number of users is n, then the total traffic is nothing but product of number of users into traffic per user, which is n times A naught. Hence, this quantity is nothing but n times A naught, and this is denoted by A. A equals n times A naught, and if I were to write this, this is A equals n times A naught, where this is the total traffic this is the number of this is the number of users and this is the per user traffic, and this is the expression that we have for the traffic in this cellular communication system. Okay. Now, for example, in the previous example, again to look at an example, for instance, consider n equals 30 users in the above system. Consider n equal to 30 users in the above system. The total traffic traffic A equals 30 A naught equals, we said the traffic per user A naught is 1 over 15 Erlang, hence this is 30 times 1 over 15 Erlang, which is equal to 2 Erlang. The total traffic in the previous system corresponding to 30 users, but the per user traffic is 1 over 15 Erlang, is nothing but 30 times 1 over 15, which is essentially 2 Erlangs of net traffic in this system. Now let us look at what is the maximum traffic that can be supported in this system. What is the maximum traffic that can be supported? What is the maximum traffic that can be supported in this system? And we consider a single communication channel. For instance, consider a single communication channel. Consider a single communication channel, then if I have one channel, I can support calls at the rate of 1 call per hour into each call for a duration of 1 hour. That is, if I have a single channel, look at the traffic I can support 1 call per hour for a duration of 1 hour, or I can support 2 calls per hour, but then I cannot support each call for a duration of 1 hour, I can support each call for a duration of half hour only. Hence, if I have one traffic channel, I can support n calls, each for a duration of 1 by nth of a time, hence I can support 1 Erlang of traffic. So speaking of a single communication channel, maximum supported traffic equals 1 call per hour into a duration of 1 hour per call, which is nothing but 1 Erlang of traffic. Hence, a single line, hence a single channel can support a maximum traffic of 1 Erlang. Hence, a single channel can support a maximum traffic of 1 Erlang, which means n channels. Hence, n channels, if let us say I have n channels, the maximum supported traffic in the cell, that is if I have n frequency bands or n time slots, the maximum supported traffic in that cell is n Erlangs. Hence, n channels can support a maximum of n Erlangs of traffic, which is essentially saying that if I have n channels, I can support a maximum of n Erlangs of traffic. All right. So that is how we measure traffic. We looked at different ways. We looked at how do we measure the traffic. Traffic is nothing but per user, it is average call duration, call rate into average call duration, and total traffic is number of users into the average per user traffic, and the maximum supported traffic per channel is 1 Erlang, which means if you have n channels, it is n Erlangs. Okay. Now we want to go into the teletraffic modeling aspect, that is how do you actually model this teletraffic system modeling. So let us go into we want to go into the teletraffic system modeling. Assume a random variable. So now we are going to, since we said the call processes, the probable that these call events are random, now we have to start off with a random, a framework, a probability based framework to model these call processes. Hence assume a random Poisson call arrival process. So we start with a fundamental assumption. Assume a random call arrival process modeled by the Poisson distribution. Modeled by the Poisson distribution. This is modeled by the Poisson distribution. This is modeled by the Poisson distribution. Okay, so this call arrival process is modeled by the Poisson distribution, and one critical aspect of the Poisson distribution is the Poisson parameter lambda, which is nothing but the call arrival rate. Hence, we denote this call arrival rate. Let the average call arrival rate in this system So, we are denoting the average call arrival rate in this system by the Poisson parameter lambda. That is, what we are saying is the calls are arriving in this system at a rate of lambda at the base station. That is, essentially the users are placing calls, and these calls, if you look at it from the base station, you say this approximately roughly lambda calls are arriving per unit time. This is known as the Poisson parameter, or essentially in this system specifically this is the call arrival rate. Hence, as per the Poisson distribution, the probability that k calls arrive at the base station in a time t is given as follows. Hence, as per Poisson distribution, the probability that k calls arrive in a time duration t is given as the probability that k calls arrive in this time duration t, that is from 0 to t, is given as probability of k, that is k calls arriving, which is equal to lambda t to the power of k e to the power of minus lambda t divided by k factorial. This is the essentially the expression for the Poisson distribution with parameter lambda, which is nothing but the call arrival rate. We are saying that the probability that k calls arrive in this time interval t is nothing but lambda t to the power of k e to the power of minus lambda t divided by k factorial. That is nothing but the probability that k calls arrive in this time duration t. All right, and hence you can see that this is nothing but the Poisson distribution. This is nothing but the Poisson distribution, and it is defined at discrete points. That is, it is defined for 1 call, 2 calls, so on up to so forth, n calls and so on. It is defined only for, it is a discrete distribution. It is a discrete distribution defined for all right, right? It is a discrete distribution which is defined for k equals 0, 1, infinity and so on. Alright, so what we are doing is we are trying to characterize this call arrival process, which is a fundamental part of any wireless communication system or wireless cellular system, and we are saying this is Poisson distribution, which is a discrete distribution and is defined for k equals 0, 1 up to infinity, and the probability that k calls arrive in this time interval t is nothing but lambda t to the power of k e power minus lambda t divided by k factorial. With this, let us end this lecture and continue from here in the next lecture. Thank you very much.